We're live.
Live at the moment.
Yeah.
Well, how do we get there?
How do we get to the molten salt reactor?
Yeah, it makes me think of, I don't know how many years ago it was. Somehow, I remember where I was. I was at the Shamrock on 112th and Pack.
Yeah.
And I don't know, maybe I returned a call of yours. And we talked for a while, and I was just in the back. And we ended up, I think I was asking you about thorium. And we ended up doing a lot of cosmology to get to thorium.
Oh, like stellar
Yeah,
nucleosynthesis?
That's right.
Sure. We could start there.
I don't know if that's necessary or not, but it was a long time ago, but
That could be, yeah, that's a good start.
sort of a chemistry / astro
Right.
cosmology
Right.
lesson.
Okay, fair enough. So
what's thorium, I guess?
Okay.
Would be
So the universe used to be pretty much hydrogen only as far as elements went, going back to the Big Bang and all.
Right. Was it anything before hydrogen? Was it like plasma? And then...
Well, now you're talking about time before time, pretty much.
Okay.
When the entire universe, all energy, matter, and space was smaller than a orange, or even smaller than a neutron. But so let's get to the point where
although
matter.
Space is smaller. It's hard to
Yeah,
compare it to something that exists within space. But
Let's talk about infinity.
Yeah, let's start with hydrogen then.
Okay, so hydrogen and helium used to be pretty much all the matter. Where do heavier elements come from? You know, they come from stars and nuclear fusion.
Right. So, if I'm trying to get a picture of like the very beginning.
Right.
So it's a
Mostly homogeneous.
homogeneous. So what we have is atoms made of
one proton
and one neutron.
One proton and one electron.
Oh, okay.
Yeah. So
That's when everything's hydrogen.
yeah, pretty much.
And nothing is, of course, as soon as it's out there, gravity starts working. But for a moment, everything's spread out.
Right. Yes.
Then things that happen to be closer to one another,
Coalesce.
randomly.
The earliest stars in the universe are really weird because that type of star doesn't exist anymore because there were no heavy elements. It was pretty much a star that's only hydrogen and helium. They were incredibly big. They burned through their fuel incredibly quickly. They only lasted like 1 or 2 million years with an M.
Okay.
Not, 6 billion years or 5 billion years for just our star.
This is generation 1.
Yes. So in the core of a star, nuclear fusion, the energy and pressure is so intense that nuclear fusion is making heavier and heavier elements.
Right.
Helium to beryllium, carbon, all the way up until iron. Because in the there's multiple different cycles.
Okay.
And this is actually very well understood, believe it or not, even though nobody's ever been there. You can't put on a suit
No one that we've met.
and take a sample.
No one that we've met.
Yeah.
Been there.
Yeah. Marie Curie, actually, that's how she did her thing.
Oh, nice.
Yeah, she took a trip to
Right. So, the way the smaller elements combine, you say it's well understood.
Very.
But it can be a 3 and a 2.
Yes.
Or a
Yes.
5 and a 1.
Yes, it's even to the point of like, well, there's in this type of star, there's the carbon boron something. Okay. I'm wrong about that, but
Right.
I could look it up in 1 second. And then there's other pathways of. It's not.
Is this chemistry?
No, it's nuclear synthesis.
Okay.
Nucleosynthesis, stellar nucleosynthesis.
So there are ways that elements want to combine in the core of a star to make
Yes,
different elements.
Yes, but it's not chemistry. Chemistry is what happens with the electron shell.
Right.
It's too hot and too dense for electrons to be doing anything except zipping around.
That's what plasma is.
Yes.
Is the electrons are
Unbound.
not affiliated with nuclei, basically.
Yeah. There's a lot going on, but it's not like our middle world of low temperature
Right.
chemical,
Right.
you know. They always make the point, like, what would happen if you had a mass of bananas as big as the sun? What would happen? It would turn into the sun.
Right.
The gravity's so intense, you know. So,
Huh.
fusion releases energy. It is exothermic up until iron.
Oh, interesting.
Yes. That's why it's releasing more energy, and that's why the star doesn't collapse into a black hole. So much energy is being released from the fusion, it's pushing out against the gravity.
That's gravity, right?
Yes.
Of itself.
Right. So if you're a star, you're going, hey, I get so much return on investment when my hydrogen becomes a helium.
I love it.
Yeah.
Okay.
Man, I have so much excess energy. Helium to carbon, not so much. It's a bit less.
But I'm still gaining.
I'm still gaining. It's still net positive.
Right.
But it's a bit less.
Gotcha. The best money is in
The best money is
the helium.
Yeah.
Okay.
And now the star goes, okay, I've fused to my iron. Now what? You know, I'm not getting any net energy. If something fuses inside the star because it's so dense, iron fuses to something higher, it's actually going to absorb net energy from the surroundings.
It gets colder.
It gets colder. Yeah, that's the way to think about
Does
it.
it get smaller? Colder and smaller? Or
The nucleus gets bigger.
Uh-huh.
The star would get they actually get bigger when they get colder.
Okay.
That's a different question.
Doesn't really matter. Yeah. But they do get colder.
Yeah, they do. It's reducing energy.
I should know it. What's iron? What's the atomic weight of a...
18 at the number? No, I don't know. I failed. But that's why iron is so abundant in the world, and and by the world I mean the universe. Sorry.
Okay, you're right. Not Terra or...
Atomic number 26. So it has 26 protons.
Okay.
Okay, so
Anything with more protons than iron
is going to cost you energetically if you're going
to put together.
To put together, yes. So to the left, lighter elements on the periodic table, net positive up until iron. To the right of it, so to speak, heavier stuff. If you're going to make it from something smaller, it's going to cost you.
Gotcha.
Okay.
But it happens because of the environment of the core of the star, the pressure and the heat.
Yes.
Fusion continues to happen, but now it's taking heat rather than adding heat.
One thing I think to kind of, because we're humans and because we live in a world where we're always taking something cold and applying heat from the external environment, we go, that's how we think of it, as if heat is a narrative. There's no heat, and then we apply it, and that causes the change. The star is generating its own heat just by the fact that it's crushing all this matter very close together. The same reason the center of our Earth is very hot. A lot of it is residual.
It's a gravity engine.
It's a gravity engine. Yeah,
Right.
yeah.
It takes mass and the force of the universe, gravity, and puts out energy.
Think of it this way: a gaseous nebula of dust and gas is extremely cold.
Yeah.
Let's say it has 2 times the mass of the sun. This big cloud of an enormous area. It might be the size of half of our solar system. A nebula, right? So cold, super cold. If I take all that matter and stick it all together because I'm gravity and that's what matter does, now it's suddenly incredibly hot. Well, where'd the heat come from? You can't think of it in terms of a narrative the way we do.
Right.
I turn on my stove and I made a star. No, it's not like that on my stovetop. So if you're a regular star, quote regular, like our sun, you burn your lighter elements to iron.
Okay.
Now you're stuck.
Right, you burn them.
Quote. Yeah. By burn, I mean nuclear fusion.
Right.
Burn is the verb we kind of have. I fuse them. I fuse them into iron. Now what? I need more energy. My gravity is the same. You don't lose the gravity.
Right, because the mass is the same.
The mass is still there.
Yeah.
Oh, shit. I have less and less energy over time.
To combat the gravity.
I'm on the clock. every year there's a little less
Dead star walking.
dead star walking. I'm running out of fuel. It's like a big fat guy who can't eat anymore, right? He has to go just on what he has available. He's getting skinnier means less bang for your buck. Yeah.
Thinner.
And they say you will actually, in stars bigger than our own, you actually get these shells almost like an onion of like lighter out, like silicon.
Whoa, like a gobstopper.
Yeah, hydrogen and helium more on the outside, and then because the heavier elements are pulled by gravity towards the center.
Interesting.
Okay.
So at the center of a star,
Iron.
is it gaseous iron?
It's plasma.
Okay,
Iron
so it's
plasma.
still plasma.
It has to be. Yeah.
Okay.
It's not a solid object.
We put these nuclei together.
Yeah.
And with larger numbers of protons.
See, we need.
But
This is
the
why
electrons are still going everywhere. It
Yes.
doesn't look like iron to me.
No, it doesn't. This is why we have to train kids at a younger age to encounter elements and phases of matter that we don't normally encounter in daily life, just to give them the vocabulary. A star is not a solid object, but that center of the star is more dense than any matter you have ever encountered. But it is not a solid.
It's not solid.
It's a liquid plasma. You know what I mean?
Right. I remember being a kid and, I don't think they talked about plasma in elementary school, but they might have mentioned it in middle school, and you knew there were 3, I think they said phases.
Right.
And you knew there were 4. They told you there was plasma, but
Right.
no one told you what plasma. I don't think it was until,
Yeah.
in the last year or
Yeah.
5 where
Yeah.
I realized what that phase of matter
Yeah.
meant.
Yeah.
Oh, it just means the electrons aren't.
Yeah. And think of it like solid, liquid, gas. Okay. What's the most abundant form of regular matter in the universe? Plasma, because of so much mass in the stars. So it's neither a liquid nor a gas nor a solid. It's a plasma.
What would it be like? Molten. Okay, water,
Right.
a molecule,
Yeah.
more than one element, which means more than one nucleus,
Yes.
right?
Yes.
That couldn't be plasma
No.
because it would just
It would break
turn into its constituent.
hydrogen and oxygen.
Right.
Yeah.
Okay,
So
gotcha.
So the star is on the clock the moment it starts its fusion of turning hydrogen and helium into heavier and heavier elements up until iron.
Right.
And once the iron, what do? When you're young, the amount of energy flowing out of the star from your fusion is far greater and able to counteract the gravity pushing it in. Mm-hmm. It's growing less, though. Those arrows are starting to become the same size.
Right.
The gravity is pretty much always the same size, but that arrow of energy pushing out is getting less and less and less over time. Now they're starting to equalize. What do you do if they're exactly equal? Well, now you're at equilibrium. Okay, cool. But you're still on the clock. You're still undergoing fusion.
Fusion's still happening,
Right?
Because of the mass and the gravity in the core of the star,
Right.
and
Right.
and all the things that
Yeah.
related,
Yeah.
pressure and heat,
Right.
that come from the mass.
Yes. Pressure, heat. Yes. Yeah. And this is when you get to the end of a star's regular life, and depending on how big the star was and how much other heavy elements it had from the beginning, maybe. So eventually gravity wins. If the star is really, really big, the outer layers shed and the inner layers collapse into a black hole. The gravity becomes so intense, you get a singularity.
How did that outer layers shed? How does that happen?
Those big stars are so fucking big. The outside is almost more like an atmosphere, and it just goes
It's so
out
far
into
away
space.
from the
Swear to
center
God.
of gravity.
Yeah, it's so strange.
Weird.
And please understand, I don't fully understand this.
Okay.
This is everybody else's. This is all hearsay. So
I heard this on the street.
yeah, that dude
I
told me.
think I heard someone mention it the other day. Did you know that when a star gets so big?
Did you hear?
Yeah.
Did you hear what she said about stellar nuclear synthesis? Or if it's a slightly smaller star and the force of gravity isn't so great, it turns into neutron, neutronium, neutron star. But then the smaller star like our own, so when this collapse happens, in whether it's a huge star or not, in a very short period of time, like a couple of seconds, a lot goes on.
This is at the very end of the.
This is at the moment.
Wait.
This is at the moment when the gravity overwhelms the energy pushing out.
Now the iron, the introduction of iron was a long time ago. We've been hanging around, building heavier and heavier elements.
Yes.
But this is at the very end when finally our energy
runs out.
Our heat.
Yes, and it doesn't run out. The energy can't go anywhere, but it's not enough to counteract the gravity.
Right.
So the gravity now crushes down.
Right. This is dependent on the mass of the star when this would happen.
Yes, it does. There's a lot of diversity in stars.
Right.
There's a whole lot. Don't ever think that ours is called main sequence for certain reasons. The most abundant one is called the red dwarf. Red dwarfs are really weird because they're so small. Some of them aren't much bigger than Jupiter. They actually they can fully mix convection currents. Their surface can exchange with the center because they're so small. Whereas our star, the layers of the material are more like they can't mix.
Gotcha. Concentric.
Yeah, kind of circles. Yeah, right. So here you have iron. You have like a plasma of iron in the core, and then in the outer layer, the helium is turning into carbon, and then above that, the hydrogen is turning into the helium. It's nuts. So in those moments of gravitational collapse, nova, supernova, this sort of thing, a lot goes on very quickly. Stellar masses of matter are crushing in, collapsing in, fusing with other matter because it's still incredibly hot.
Whoa.
Colossal amounts of energy are getting ejected. Because of the fusion, yes.
So it goes, but while it goes, fusion's happening.
But is the fusion releasing energy? Is it exothermic or is it endothermic or is it both? That's what I mean. Like in 30 seconds, a star the size of the Earth's orbit might collapse into a black hole, dude.
The size of a golf ball or a...
Well, I mean, a singularity is technically infinitely small. No, if it's a neutron star, it might be...
We talked about different sizes of black holes, though.
Yes.
It doesn't matter. Yeah.
So a lot is going on. A whole lot. Like stellar masses of interactions are happening. And you have something called... The normal nucleosynthesis we were talking about is there's slow neutron capture, where you're a nucleus of an atom bebopping around for a million years, a billion years.
I might be helium, I might be carbon,
and I get hit by a neutron, and maybe it turns me into something else, or maybe it makes me unstable and makes me split. That's a slow neutron capture, where the evolution of a nucleus of an atom can do kind of what it wants because it gets hit by a neutron and then that unbalances it and then it can turn into what it wants to be thermodynamically.
Okay.
Because it's going to stay inside that environment of the star for maybe thousands of years.
Okay.
Right? But at the moment of collapse, during a nova or a supernova, all of a sudden there's this insane environment where neutrons and electrons and photons are interacting at insane temperature and pressure, and that causes something called rapid neutron capture.
Did you mean protons or did you mean photons?
Photons, protons, neutrons, everything. You have to understand that these conditions are nothing like any other
the universe most of the time.
Those conditions, while it's collapsing, are more intense than what's, quote, normally going on in the core of a star.
Right.
This is pressure and neutron flux. Neutron flux only means the density of neutrons flowing through a given space at a certain amount of time.
Okay.
Like the flow of water, the flow of neutrons. So you think the center of the Earth is intense? nothing compared to this moment. So during this moment, all of a sudden, an iron molecule, and the iron nucleus that might have been hanging out in
the
the
two mostly protons
protons and neutrons.
and neutrons. Okay,
Yes.
because earlier you seemed proton-centric.
That's for hydrogen. That's just for hydrogen.
Okay.
You're an iron nucleus, and you've been at the core of the sun for, let's say you were formed 869,000 years ago.
Mm-hmm.
And you've been leading a peaceful coexistence
With everybody else.
with everybody else
in the core.
in the core of a star. Now all of a sudden,
Sure, it's crowded, but it's
Right.
It's nice.
this is how we get elements heavier than iron. This is where it comes from. Up until now, we're pretty much only talking about stuff that lighter than iron.
Oh, so the fusion that continues to happen after iron's around is everything still
Accidental.
just getting up to
Still
iron?
just getting up to iron.
What does it? Okay.
You might occasionally get something heavier than iron,
Okay.
but it's not hot and dense and energetic enough to make very much of it.
Got it.
And it's a negative feedback because it absorbs it from the environment. And so, the iron got hit by a neutron or a proton, and maybe it interacted, but it's really not going to happen that much,
You do get some heavier elements.
A little, but it's-
normal.
Yes.
The I don't know what to call it. The second
Nucleosynthesis.
half.
Yeah.
Second half of the life of the star. There's still fusion bigger than iron happening.
But it's vanishingly
not
rare.
much.
Not much.
Gotcha.
But at that moment of supernova,
I see.
that iron nucleus is like, I mean, it's just like, and in a millisecond or two, that iron nucleus during the process of rapid neutron capture might capture so many neutrons and protons, maybe, that all of a sudden it's uranium.
Gotcha.
You know what I mean?
And
Or anything heavier.
Now, earlier you were saying that this process, the fusion process, is pretty well understood in the core of a star.
Fairly, yes.
Were you talking about sort of through the normal life of the star, or are you
The
saying,
normal life of the star, yeah.
Do we very well understand in what ratios we get certain elements from certain nova?
Oh, that's a
events
really good
or
question.
Supernova events?
Oh,
Like,
man.
is it all bets are off? Kind of I mean, it's probably not random, but we get this amount of uranium and this amount of this and this amount of that, or
That's a really,
what?
I've never thought of that. You should ask that to a physicist. I haven't encountered it because it's,
Yeah, we had one scheduled, but
yeah, darn.
he had to be somewhere else.
With nuclear stuff, it's statistical based.
Okay.
So because you're looking at so many, if I had a little dice-sized piece of uranium, that's trillions of atoms, you know? So the statistics are what bear it out, and the math works. But there is yeah, I know.
mean, yeah, if I'm just not being a physicist either,
Right.
but if I had to guess, I would imagine the variables would be the sort of how old the star is and how massive the star is,
And its recipe.
and how exactly, and how those things
Yeah.
resulted in
Yeah.
whatever was in its core
Yeah.
and outer shells
I think
when it
you're-
finally supernovaed.
I think you're right. If you knew, they call it metallicity, everything, and it's kind of a misnomer unless you're an astrophysicist, I suppose. Everything heavier than hydrogen, I think, is called a metal. And so the more the metallicity of a star is, it's how much of the stuff from the beginning, how much boron and lithium did it scoop up from space while it was being formed?
Right.
The gas
Because
cloud that
right,
formed
we
it.
started
Yes.
with the first generation, which was
Pure hydrogen.
pure hydrogen, but that's not the only flavor
Right.
of star.
Right. So here we go. So when they go nova, when they go supernova, they'll explode and they'll eject, and now all of a sudden, in milliseconds, something that was mostly iron and everything lighter than it is now a lot of iron and things lighter than it, but it's also things like uranium
Or
or thorium or lead or bismuth or antimony.
right, yeah.
Where did the periodic table come from? all it is counting element 1, element 2, element 3.
Mendeleev?
Mendeleev, yeah.
Not to be confused with Mendel. I always do that.
Yeah. I'll tie it in with him.
Punnett square?
Yeah.
Is that him?
I don't know. Punnett squares?
No, what are they called?
Punnett squares. Yeah. I don't know.
Peas. You know, the monk with the peas and genetics.
Oh God. Fuck off. Okay. So all those heavier elements, in a matter of very short amount of time, explode into outer space.
Oh, that's interesting.
Because they're brand new.
Okay.
They're brand spanking new.
But how do they get out?
Because in that process of going supernova, a tremendous amount of energy crushes in, and then it explodes out again.
Yeah, some of it.
Also, what's happening is
some of it remains to be
a neutron star, maybe,
or a black hole,
or a black hole, or a white dwarf.
Okay. Oh, so stars can nova or supernova and then end up still a star, but of a different flavor?
Sometimes, yes.
Okay.
I
don't think I knew that.
They call it a neutron star, but it's not undergoing fusion, but it has a tremendous and an absolutely astonishing amount of residual heat trapped in it, even though it's so dense it doesn't even have protons.
What?
Bro.
So it's all
Where's
electrons and neutrons?
No electrons.
Just neutrons.
Just neutrons.
That
you can go from something...
That doesn't seem allowed.
They shouldn't... It's like, okay.
And then they just hang out there?
Some of them...
But no fusion happens.
No fusion.
Wait. But they're still producing heat and light because we can see them.
Yes. And why don't they collapse into a black hole, Luke?
I don't know. Do neutrons have... Well, neutrons must have mass.
They have mass. What counteracts gravity? This is your lesson.
Energy?
Yes.
Heat?
Yes. So if the heat is residual and it's just it can only get colder because there's no fusion that can happen.
Heat is just stuff bouncing around, right?
Heat is the average kinetic energy, so that couldn't do it, could it? Neutron degeneracy pressure. Any heavier than that and it turns into a black hole.
Degeneracy pressure. Does that mean
you also have
neutrons sometimes blip out of existence, but then...
No, unless... Well, yeah. Well, you're right. They do dip out.
It's called a degeneracy, so I'm imagining a neutron just going...
Right.
But that maybe...
A neutron can touch another neutron because they have no electric charge. Before
hence
that, you...
the name.
Hence the name.
Yeah.
Before that, you have electron degeneracy pressure. Normal matter, protons and neutrons in this tiny nucleus, but the electrons repel.
Right, okay.
Gravity can overcome electron degeneracy pressure, basically crush them down into the protons and turn them into neutrons, and now the neutrons are touching.
Wait, what?
And repelling each other.
Electrons can become neutrons? Is that what you're telling me?
No, electrons can combine with a proton and become a neutron.
Okay.
Don't ask me how.
Is it 1-to-1 or... Probably not.
You're getting into... Well, they actually hypothesize a quark neutron star that's actually even lower than a neutron, but I don't think they've observed it yet.
Right.
But the math is there.
Now, okay, so when we're in... Not to get sidetracked, but... I don't even know if we'll make it to the melter.
We might not.
Which is fine with
We
me.
can hold it. We can hold that one for mugs if we want. This is the intro.
Yeah, I like this stuff.
Yeah.
As an interested layman. But
Yeah.
So, okay, when we're kids, we know, an atom is made up of protons, neutrons, and electrons.
Yes.
Right? The nucleus is made up of a glob of protons and neutrons, generally of equal number.
Yes.
That's what we're told, or that's what I remember.
Mostly.
And then we've got electrons orbiting
Yes.
the nucleus for some reason. They orbit.
Well, I mean, they're attracted to the positive charge of the protons.
Right.
That's what holds them.
Well,
They're lassoed.
Right, but what, as a kid, I was like, well, if they're attracted, why don't they just go stick to the nucleus? Because I know how to play with magnets, and if this one's positive and this one's negative,
right?
Well, they want to touch each other. They don't want to hang out at a fixed distance.
Right. They can't because they're too small and energetic, and that's why you have electron orbital clouds.
Right.
I mean, think of it this way.
Valence shells or whatever.
Yeah, that's why.
But yeah, I never understood. Well, if this is positive and this is negative, why don't they just cuddle?
Well, if the gravitational field is strong enough, they can.
Really?
That's a neutron star. The protons have been destroyed, so to speak, by gravity forcing the electrons to interact with them and turn them into neutrons.
Okay, right. Oh, that's what I was getting. So, like that, when you're in middle school and in high school, pretty much you've got your subatomic particles are of three types: protons, neutrons, and electrons.
Yeah.
Later, if you're interested, or if
Right.
you continue to study physics, you
boy.
realize that those things are made up of constituent parts.
Right.
Are each of those three things made up of smaller parts? Is an electron made up of smaller parts?
No, as far as I know.
Oh, but protons and neutrons are.
Yes.
Right.
Yes. Quarks.
Quarks or
Yeah.
muons or gluons or
Muons. Well, no, I don't know muon. I don't know that. Quarks.
Okay.
It's just saying.
But as far as we know, electrons aren't made of things.
Electrons seem to be a fundamental particle.
Okay.
Right.
So on the same hierarchical level as a quark.
Yes.
Okay.
Yeah.
Great. Thank you for the clarification.
So now a star has burned through its... Here's a newborn star crying.
Yeah.
You know?
Cigars all around.
Cigars all around. Congratulations. You have this much gravity and you have this much fuel. That's your lifetime.
Right, and they're both dependent on the same.
Yeah.
The mass.
What created you? You know,
I guess
what you
the
are made
fuel
of.
would be dependent on actually your recipe, like
Yes.
you mentioned.
Yeah.
Not just the mass.
One reason our star is so stable in more than one way and given a very long life is because it's like a second or third generation star. When it was made, the gas cloud recipe that was its parent
Right.
was already enriched with other elements from
supernova
other earlier
and supernova
that
events.
exploded, billions of years ago. That helped stabilize it.
Interesting. Oh, okay. Interesting.
Yeah, they are higher in metallicity.
Okay. If you were an astrophysicist, you could categorize the flavors of stars by what they're made of and their expected lifetime.
Yes. Yeah, you could. You really could.
What they're made of and their mass, I guess.
Yes.
Would be another variable.
Yeah.
But given what they're made of and their mass, you could say, that's probably going to burn for X amount of years.
Yeah.
If you were an astrophysicist.
Truly. Yeah.
Okay. Gotcha.
And at the lower end of it, so our star and
what's
others.
our star like? I don't know anything about it. How old is it?
It's about It's about 5 billion years old. It formed at the same time as the Earth in the same thing.
That's interesting.
Right.
How about the other planets? Are they all about the same age?
Yeah, we're all about the same age.
Solar system, the star and its friends all sort of coalesced around the same time.
We're one big family.
That's interesting.
We're all children of the same gas cloud that came from other stars that lived and died.
Right.
I don't know where
not the original gas cloud that was all hydrogen.
Not Big Bang gas cloud, no.
Right.
Although there were undoubtedly some things in it from the Big Bang.
Right.
And we do have some visitors.
And I'm breathing Caesar or whatever.
Yeah. You can't think of this in terms of cause and effect. It's happening. The planet is forming as part of the interstellar disk around a star that is forming under its own gravity.
Now, that's funny, because I wouldn't say that's entirely intuitive.
You have to get beyond time, I suppose, since we're talking about Big Bang and black holes and shit. But
yeah, right. But I'm imagining,
I
know about gravity, and I can say that. I can think about gravity and think. Well, let's think two-dimensionally, right? Let's say I throw a bunch of marbles on the table, and at first they're scattered roughly evenly around the table, but they happen to have areas of more density here
Yes.
and there. So I can imagine, all right, well, if marbles want to be together, then this long gradual process happens where they
Yes.
clump up.
Yes.
Um,
Yes.
and then you end up with stars or planets, I guess,
Yeah.
later.
But what you must not do.
But why would the planets and stars happen at the same time in the same area?
What you must not do is have the narrative of the sun formed and then it caused the planets to form.
Right.
What you might not.
Sense.
Right. And what you must not do is think of gravity in terms of a narrative of like, oh, there's a center and then it causes that. No, the center and the edge of gravity are contiguous. They're continuous. They've always been orbiting each other. It was always there. It didn't form and then the gravity acted.
Right. They
Right. So the same gas cloud that the Earth came from was part of the same gas cloud that the sun came from.
Now, does it happen that stars, and I'm sure that it does, but does it happen that stars coalesce without planets around them?
Oh, yeah.
Does it happen that planets coalesce without stars around them?
Yes, that's one of the more exciting aspects right now.
Lonely planets.
Dude, there are, okay, please, people who are,
So it's a cloud of heavy stuff in space.
now that our satellites are getting better, we are finding so much cool shit that they never even dreamed of. And I'm talking like the science fiction. I'm talking like the physicist who takes mushrooms and LSD at the same time. And for the audience out there, people who are worried about our own lonely spot, there are something like 1.6 planets to all the stars in the universe. That is such a lovely thing to know.
Huh.
That the ratio is higher. There's more planets.
Than stars.
Yes. Most stars are binary. There's two of them.
Most stars.
Most stars have a partner star.
It's a special case.
No, that's the norm. We are weird.
Weird.
Yeah.
Whoa.
Dude, it's so cool.
Most stars are binary. Do binary stars have planetary systems?
Some
Some of them and some of them
don't. You'll have instances where the one partner goes nova and turns into a white dwarf or a neutron star, but his friend doesn't, his partner. And he'll sit there and suck gas from the outer layers of his partner.
Right.
Well, if you're
Bigger.
No. Well, okay, yes, but if you're a neutron star or a white dwarf, you're in trouble because you're increasing your mass. And you're already barely holding above being a black hole anyway. Increase the mass a little bit, and you're a neutron star, you're in danger of becoming a black hole. If that's a bad thing. Maybe that's a form of ascension. I don't know. It's and you'll sit there and it will suck up enough gas from the outer layer of its partner star until it ignites fusion and then blows off the outer layers because the forces involved unfathomable.
We call that nova?
It can't. Yeah, it's weird.
Is it collapsing when it blows off its outer layers? Or does it just blow off its outer layers and continue to be a
neutron star? That seems to be more. If you took a normal piece of matter, let's say the pen you're holding, and you dropped it onto a neutron star, it would accelerate as it approached the surface because there is a solid surface on a neutron star.
solid? You mean not plasma?
More solid than anything solid you've ever seen. It's weird. It's kind of like a form of plasma, but there's no electric charge because it's neutrons. It would accelerate to very close to the speed of light. It would impact the surface and spread to a layer as thin as an atomic nucleus because of the gravity.
Instantly.
Almost instantly. Yeah. If you had a snooze canister size of neutronium from a neutron star, number one, it would weigh more than like the Himalayas.
So neutronium is not an element, but it's a type of matter.
Correct. It's not an element.
Made
It's
of neutrons.
yes.
Whoa.
And if I dropped it,
What?
if I dropped it, it would fall and accelerate towards the center of the Earth because it's not electrically interacting with
Oh,
anything.
it go through everything.
It go through everything.
There's no electrons.
There's no electric repulsion. There's no Pauli exclusion principle, I think, and it would accelerate towards the Earth's core.
Couldn't it hit other neutrons on the way?
I don't know. I don't know.
I mean, this table's got a lot of neutrons in it.
It would, well, what it would do is it would suck in all the matter. You'd have this weird kind of funnel effect of it basically pulling. It'd be like the destruction of the planet in that J.J. Abrams Star Trek thing, except it wouldn't be a black hole. It would rip the Earth apart.
Really?
Yes.
It'd be extremely massive.
It would be more massive than the Earth itself.
Oh,
maybe
okay.
not that much. So
it would grab stuff on the way.
only with gravity.
Right, with gravity.
Yeah.
Right.
Yeah. Anyway, so where the fuck? Neutronium. I think it's called. Yeah, it's got to be neutronium.
We're back to Futurama.
Yeah. Right.
I'd never heard of such a thing.
It's pretty cool. Yep. It's neutronium. I was right about that.
Atomic weight 0 or infinity or not applicable. Na.
Well, and they think that in the center of a neutron star you have shit like it's sort of a plasma. It's something liquid.
But there's no electrons.
There's no electrons. Don't even add, because liquid. What the fuck?
It's got to be made of something.
Well, what's really cool is they can absorb because stars are spinning. So during that supernova process, insane shit is going on, and you have quasars, pulsars, where the forces involved as they're collapsing, they're also spinning. And since you have the conservation of angular momentum, it gets sucked down and it's getting pulled along gravity and gets shot in this incredible spiral called a gamma ray burst that can sit there
in poles.
Yeah, the poles of the star. And if you're a life-supporting planet very far away, like in the same galaxy far away, don't be in the path of a gamma ray burst because it can destroy your atmosphere in a second.
What?
It's like an intergalactic death ray. Yes, the power. It's so like this is our world.
But it doesn't happen for very long.
No, it doesn't happen for very. It's a burst, gamma ray burst.
Okay, you said quasars, right?
I don't know what a quasar is.
Pulsars.
Pulsars are neutron stars that have done that, and they're sitting there spinning so quickly, they are shooting like radio waves out across the universe.
Not gamma ray, not gamma death ray.
No, the gamma death ray happens at first, but since there's no more fusion going on, all the energy is relic energy.
Okay, we do this probably every time we get together.
Yeah,
but what's gamma radiation again?
Extremely, extremely energetic photons.
Photons.
The light that you and I see, if I took those photons and juiced them up, it'd be gamma rays.
But the pulsar is just sending...
A pulsar is a pulsating neutron star.
Right, okay.
A neutron star that's sending pulsating like radio waves or whatever. But because
they've confused us before.
We thought it was aliens.
Right, exactly. Because it was a regular bleep.
Yeah.
A bleep at a regular interval.
Yes, yeah.
So that was just photons again, but less energetic?
Yeah.
You said radio waves, that's electromagnetic spectrum.
Correct.
Right.
Because the neutron star can't get any more energy, so it slowly gets less energetic.
It's still spinning, and it's still shooting off at its both poles?
Yeah. I think it would have to be both.
It's not a gamma death ray.
No.
But it's...
It might have been when it first started, but now
Gotcha.
Yeah.
So we if we can hear it, then we
Yeah.
It was a close miss. We almost got gamma death rayed.
Well, maybe it might have been a close miss a billion years ago.
Right.
So,
yeah.
Which in terms of the universe,
pretty close.
Yeah. So
frog's hair.
Yeah. So because of stars, the universe is seeded with elements heavier than iron.
Right. Because they blow up and they throw them all over the place, and then sometimes they end up in other stars that blow up.
Yes.
And sometimes they end up in not stars. What? Okay. That's a good... What's the difference between the coalescing of a star and the coalescing of a planet?
Gravity. There's just not enough matter to turn it into a star.
Does it have to do with the recipe? also? Like, oh,
No.
I'm all iron and boron and uranium.
No.
I'm not going to start fusion.
Because it's fairly the
So there's just a threshold of mass
pretty much
that either makes
Yeah.
something, oh, I'm an inert, or inert for a while.
right.
I'm an inert ball of stuff,
Ju-
or I'm a fusion furnace.
Yeah, there's a type of star called a Brown's dwarf that is basically an almost star. It almost can start full nuclear fusion, but it just didn't have enough
Stuff.
matter. Yeah.
Right.
And if it collected a bit more, it might very well turn into a red dwarf.
Interesting.
Jupiter is almost a brown dwarf. It only needs a little bit more mass. And
And then
because
fusion would start in its core because
Yes.
of the pressure.
yes, Jupiter's fucking big. I think it weighs more than all the other planets combined. And I'm including Saturn and Neptune. And
See, I thought you'd exclude Saturn and Neptune when you said all the other planets.
right. And so this is actually why Pluto doesn't get to be a planet, because it's basically a asteroid that orbits the sun. There's a lot of other things like Pluto.
Right. I've heard that.
Yeah. So it's if you're
Pluto
gonna,
didn't form when the sun formed, is what you're saying.
it's just different. It didn't form the way a planet forms,
Huh.
so it doesn't belong.
Okay.
It's part of it's a distant cousin. It's still part of the solar system, but it's not a planet. Oh no!
Can't all be planets.
Right there, and yeah. So
And
yeah,
can't all be stars.
and there are cases where, I undoubtedly, not in our solar system, as far as I know, but there's a planet that orbits some star, and it's like, you came from elsewhere.
Right.
You ain't from around here.
Right,
You know.
right.
Yeah, straight up. But all of our planets, the main planets, formed with the sun as part of that process.
All the ones Holst wrote about in his Planet Suite.
I think so. Yeah.
Probably.
Yeah. What was the last one? Neptune. I think so.
I think so. Yeah.
Because Pluto hadn't been.
No.
Yeah. Cool. So I've actually seen Mercury with my bare eye. Tosh showed it to me.
Was that hard to do?
Yes. But it was the ascension was just right, and the weed was really strong.
Well, yeah, I've seen fucking.
I have those. No, I know.
I've seen Titan with my bare eye.
Right, no.
I was.
It's really something.
I went there. I visited. No.
But there's a reason the planets are all on a plane, the same line in the sky. It's like Venus, and there you could barely see it on the horizon. But it was. He really knows his astronomy. I wish he was here. But so now we have clouds of gas and dust seeded with all sorts of elements, everything from hydrogen all the way to plutonium when it's young. Some of those elements are very long-lived. They don't do anything on their own except kind of exist if you put them in a cold environment with no neutrons flying around. Others are naturally radioactive. Things like uranium, things like plutonium, things like thorium. And if you're radioactive, you are unstable in your nucleus.
Okay.
Because you're too heavy and the balance of neutrons and protons isn't quite what you want thermodynamically.
Now you said some elements are happy to just chill out,
And they're
depending
not-
on the temperature. Could any element be radioactive?
Yes.
In the right context.
Yes, because the way that you're set up the language for that, what you just described is exactly what you described if it went. You take that element that's
Nova.
super heavy, nova, put it in the middle of a
So it's
supernova.
radioactive when the nova or supernova event is happening.
Right, but when you say it, are you talking about it being lithium or it being uranium? Because what we're talking about with supernova and nova and stars exploding is one element becoming another. Yeah, it was lithium. Now it's uranium. What's the difference?
Is that what we're
Our-
talking about when we talk about a radioactive element being radioactive? It's
Yeah.
one element becoming another?
Yeah, pretty much.
Slowly?
Or swiftly, depending on the circumstances. Yeah. It was uranium. Now it's bismuth and ruthenium, or whatever it is.
Okay.
Whatever uranium splits into. So where's the uranium?
Well,
It's now two things.
right.
They
That's what being radioactive means.
Yes, radioactive decay. If I have a molecule of iron,
Is it sloughing protons or neutrons or both?
it depends. It depends. Okay? But this is we're right on track. We're not getting sidetracked by this. If I have a molecule of, let's say, carbon that's not radioactive, it will sit there happily balanced with its protons and neutrons. Whether it has electrons on the outside or not is immaterial.
Right, that's chemistry.
Yes, correct. That nucleus can sit there and be happy thermodynamically and never be radioactive, basically infinity,
Right.
ad infinitum. It won't spontaneously
Do anything.
Yeah.
Until something happened to it.
right. If I bombarded it with neutrons or whatever, yep.
Maybe.
Yeah.
If I heated it up real hot.
Incredibly hot, maybe you
Something
could
might
fuck with it.
happen.
Yeah. But it's not naturally radioactive. Aluminum, Other elements like uranium or plutonium is going to sit there and it's like, I don't...
Just aren't content.
Yeah, it partly has to do with its mass is too big and its neutrons or the balance of neutrons and protons. The thing is, protons repel each other, but neutrons don't.
Okay.
Both neutrons. So in that case, why does a nucleus hold together at all? If the protons are sitting there just wanting to rip apart.
Strong nuclear force.
Yes. So the protons have a strong nuclear force that are pulling together. But they also have a positive repulsion that's pushing them apart. The neutrons have a strong nuclear force holding it together.
And nothing pushing them apart.
Nothing that pushing them apart. So the heavier an element gets, the more neutrons it needs to hold together.
Gotcha.
And if that neutron-proton ratio is unbalanced, radioactivity.
Then the protons overcome the strong nuclear force. And they go...
It's probably not that simple, but that's the overall idea, yeah.
Interesting.
Yeah. And that's why they're always...
We're doing the weed or DMT fractal thing, right? We were talking about stars and what held them together and the forces that we're pushing out or in, and now we're...
It's all thermodynamics. This is what they mean when they say, if you're against thermodynamics, I can't help you. It's crazy.
It's turtles all...
Yeah. In a star, it's energy out versus gravity in.
Right. In a nucleus of an atom...
It's positive repulsion versus strong nuclear force. Yeah.
Gotcha.
Yeah.
Interesting.
I mean, this is...
So the smaller stuff isn't going to be bothered because the strong nuclear force has got an advantage over the number of protons that don't like each other.
Yes. And thank you, Luke. So at extremely small distances, the strong nuclear force overwhelms electromagnetic repulsion.
Gotcha.
So that's why a helium's like, boop, boo, I'm so happy, whereas...
Couldn't be
happier. Whereas plutonium's like, oh my God, I've got 239 goddamn protons who hate each other.
If I get one more of these or one less of an
I might just go and split apart. Oh no, I'm in a bomb or I'm in a nuclear reactor and now there's a neutron coming my way.
I was unstable already and now I'm being introduced to some...
Yeah, he's Mr. Creosote. He's too fat. The little wafer, it's only wafer thin. It's only a neutron. No. And he blows up. That's what happens in a nucleus. He gets... Yeah.
Now, when he blows up, can he blow up in more than one way? Can he just send one proton away? Or does he always blow up in the same way? Does he split into...
Correct.
1/3 and 2/3, or does he split into half and half, or does he split into 99 and 1?
Here we go. You're right there, man. There are multiple pathways. Sometimes, believe it or not, Mr. Creosote can sit there and eat that wafer-thin neutron, absorb it, turn that neutron into a proton and fart out an electron.
That's radiation of some sort.
That's beta decay.
Okay. And he's still
big and fat, but he just
unstable, but he's still at equilibrium.
Yes.
He's
yes.
still there.
Yes, he's still there. He has not split in two.
Takes an extra neutron.
He just ate a neutron.
Turned it into a photon.
He ate the
proton.
Turned it into a proton. He went from a neutral charge to a positive charge. And he farted out an electron, and a very energetic one. It shoots out. But now he's not plutonium anymore. He's something else. Because he took on a proton, he just increased his atomic number by 1. He is a different element. New element, new chemistry. That is called breeding in a nuclear reactor.
That's breeding.
That is breeding.
Is it always just one extra?
Yeah. Yes.
Neutron bombardment. The thing you're shooting it at turns that neutron into a proton.
Well, okay. Going back to stars, just as a brief aside, if it's happening very rapidly, the rapid neutron capture we described, then it can happen more than one. Because actually what happens is there are so many neutrons happening in that incredibly short period of time.
You can jump a couple, is what you're saying.
They turn into new elements faster than they can even emit electrons.
Whoa!
Swear to God, that's what it means.
You can go up two on the chart and only throw one electron out.
Yeah, you're just like, you're suddenly 3 trillion neutrons have gone through your nucleus in a microsecond, in less than a microsecond.
And for some reason, a few of them transform into protons.
It's just everything happens at once. You know what I mean? I couldn't begin to describe it. Like, I would love to see a physicist try to be like, what would happen?
Yeah, show me a little whiteboard cartoon.
Yeah. So if I have uranium-238, an isotope of uranium, and it gets hit by a neutron, and that neutron... The Mr. Creosote example is good. That neutron is just the right size for his little pea mouth. Maybe a 10% of the time, it might cause a split. A fission.
Like a bursting.
A fission.
Right.
This is the opposite of fusion, fission. Splitting.
Right.
Or maybe 90% of the time, if it's just the right energy, it will cause him to eat it, turn it into a proton.
Now he's gotten bigger.
Now he's not uranium-238, he's plutonium-239. The same thing happens with thorium. Thorium is another big fat radioactive element.
Right.
We don't hear much about it because it was never used in bombs.
Well, what good is it then?
Right. Well, that's what we need to get into the cultural side of this when we get to the reactor itself. The thorium sees a neutron coming and goes and eats it, and he turns in and he breeds. He transforms into uranium-233. Now, what does the uranium-233 do?
He gets another neutron, or
he splits.
Okay.
Then he splits, because you can't do it forever, even if you're a supernova going on, because that's just the basic thermodynamic laws of physics. There's a reason why there isn't an element 1,000 or 10,000. It's just a number. Just go on. Why does the periodic table peter out, both in terms of number and abundance? Why is there so much iron in the world and so little plutonium?
Because there are a few natural laws.
Yeah. You never break the chain, even when you're dealing with forces as powerful as gravity and strong nuclear force. So
there are constants, I guess, in addition to natural laws.
Yeah. If we were some hyper intelligent being that traversed the stars and just go off, whatever we wanted, probably the real events that you'd have to buy expensive tickets for to watch would be like a supernova in your specially shielded ship, because for a tenth of a millisecond during that supernova, you might see element 400.
Right.
Because it's going to form during that neutron flux and then decay instantaneously.
Right.
You know, because it just can't happen. So matter exists as this island of stability. Woo! So
Or the normal matter that
normal
we think
matter.
of as matter.
And that's what it is. We are that normal matter
Right.
of stability.
Right. I don't encounter
Right.
what did you call it?
Neutronium.
Neutronium very often.
Here's the trick question. We'll probably start when Muggs gets here. We'll start it with this one. But how many plutonium mines are there on Earth? How much plutonium have we mined during the Cold War to make our bombs? I mean, trick question.
None. We got it from mining for something else.
Yeah. We made it from uranium.
Ah.
You take uranium, you put it in a nuclear reactor, you expose it to some neutrons.
Uh-huh.
It becomes plutonium.
Is that a breeding?
Yes.
Okay.
It breeds up. U-238, uranium-238, depleted uranium.
Why did we want?
What exactly? Good
What's
question.
the difference? Why is plutonium better for a bomb than uranium?
Okay, so there are
It's just a little bigger. One or two bigger.
One.
238
plus 1 makes 239.
Okay.
Plutonium is, because of technicalities of its chemistry and its radioactivity, is very good for building a bomb.
It's just more ready to.
It's just better at it. You know what I mean? Like its recipe overall.
Uh-huh.
Because other radioactive elements are more volatile, they're more chemically active, they're more dangerous to handle.
Huh.
Really, truly. There's more than one type of plutonium, too.
And what is it that we do to make it explode? What is it that we do to make it go boom?
Right? Here we go. So
we turned uranium into plutonium by hitting it with some neutrons.
Yes.
And then now it's plutonium.
Now
what do we do with it to
Right.
make it level a city or whatever?
Right. So here we go. Another reason, just to finish that sentence, is separating things chemically with their electron shells is much easier than separating things by their very small differences in mass.
Mm.
Because if it's the same element and they're only separated by the weight of one neutron or something, how do you get those two things separate? That's what uranium enrichment is. That's what we're mad about Iran for doing. Making a bomb out of uranium-235, the fissile one, the one that splits, is not hard if you already have the uranium-235. But uranium-235 is less than 1% of uranium in the ground.
Okay. What's the difference between uranium-235 and the other flavors?
Here we go.
Number of neutrons?
Yes.
Yeah.
Yes. So chemically, it's
That's
the same.
an isotope, right?
Yes.
Right.
Yes. You got it. So if I had a sphere of uranium-238, pure uranium-238, at normal room temperature conditions, it's not inside of a reactor, okay? So it's just, it's as if it was a chunk of aluminum. Mm-hmm. It's just a piece of metal. Mm-hmm. That uranium-238 is very slightly radioactive. I could have a sphere of it as big as a basketball, and nothing would happen more it would not cause a positive feedback loop. It would not cause a radioactive event. It would just still be uranium as if it was dust.
And every once in a while, it would throw an electron at you, or?
More. It would emit radioactivity. Let's just leave it at that.
Okay.
If I had a sphere of it the size of this room, if I had a sphere the size of a beach ball, if I had an amount of it the size of a football stadium.
There's no cascade.
There's no cascading chain of events.
No positive feedback.
Correct. Yeah. If I had a sphere of uranium-235.
So that's fewer neutrons.
Fewer neutrons, yes.
Right, which means it's less capable of fighting that
Yeah, so that's
the
right.
strong nuclear force.
Yeah, that's right.
Or more capable. It wants to go out.
The neutrons
Yeah, it's
count.
better. It's better at fighting the strong nuclear force.
Yeah, that's right. You
Right.
got yeah,
That's
you got
what
it.
it is.
Yeah,
Because there's fewer neutrons.
holding it together. Neutrons hold a
Okay,
nucleus
I think
together.
I switched it again, but yeah.
Yeah.
So yeah, the electromagnetic polarity of protons wants it to go not be it,
Correct.
not
Split.
be a part or
Split.
not
Fist.
not be a party.
Fission.
Right. And strong nuclear force wants it to be a party,
Yes.
and the more neutrons you have, the more stable it is.
Yes.
Okay. Anyway,
If
so,
I
235.
So 238, I could have lumps of it together and nothing's going to happen. If I had a sphere if I had 2 half spheres of uranium-235, roughly the size of a bowling ball, nothing's going to happen.
Okay.
If I had one in each hand.
Okay.
But if I fold them together, it will start a chain reaction of fissions because the neutrons that are being emitted passively as it regularly decays are going to hit other uranium-235s, cause them to split, which releases more neutrons,
Okay.
which causes
So they they split into smaller elements.
They split into smaller elements, but it happens very quickly.
Okay.
And so it causes a chain reaction. And if that chain reaction happens just right, it's a bomb. It's an atomic bomb.
And this is, but in stars,
It's different.
fusion released energy.
Correct.
In this case, it's fission
Why?
that's releasing energy.
Correct. Why? Think of iron again.
Well, when you put it together, things got colder. It took energy to put iron together,
All the way to iron.
all the way to iron.
Up until iron, it releases energy.
Right, and
Past iron,
it takes energy.
takes energy.
Right.
So you're releasing the energy that was absorbed during a supernova. It's that curve.
We're on the other side of it.
We're on the other side of the curve.
So it makes sense that. Well, yeah. Okay.
Supernovas.
Right. We expended energy to make anything larger than iron.
Yes.
So fusion up to iron is exothermic.
Yes.
Fission after iron is exothermic.
That's right. You got it. Nature harvested the energy of supernovas and stored it
In these big elements.
in plutonium, uranium, thorium,
In the nuclei.
in the nucleus itself. That's the only place you could have an energy source that intense.
That's crazy. Because, when we're, again, back to my, I enjoyed the study of this stuff
Yeah.
when I was a kid, but
Yeah.
never, the only
Yes.
proper natural science class I took at school was musical acoustics, and I slept through a lot of it. But, thinking about like chemical bonds, right?
Right.
We learn about that in high
Right.
school. Like, oh yeah, energy is stored in chemical bonds. You
Hold on to that.
You when you break chemical bonds, you get energy.
Right.
But this is deeper than that. It's
Far deeper.
Nuclear bonds.
Nuclear bonds are 1,000,000 times more potent than chemical bonds.
Right. Fuck electrons.
Why does burning a lump of coal release energy? Why do we do it? Why is there all this heat if you combine it with oxygen? Well, the reason why is the electron is happier next to a that's right. An electron is happier next to an oxygen than it is to a carbon. And so it releases a little bit of energy. It's thermodynamic. And we take that energy and we turn it into steam, and we use that steam to drive a turbine, and that's how we power our civilization. Well, if you have they make the point, the people who understand this, because there's a little bit of uranium and thorium inside of coal.
Huh.
There is uranium inside of your body right now.
What's it doing? Hanging out.
hanging out because you absorbed it from your surroundings, because you're a part of the earth. There's uranium in my left hand. There's a few atoms in there. Let's somewhere, yeah. Let's hope they don't give me cancer.
Are they radioactive?
Slightly.
Wow.
Maybe a billion years from now, the uranium that was in your hand, when it's in your descendant's hand,
will release a...
Yeah, it might.
Because
Because most uranium is not very radioactive. So there's uranium and thorium in coal deposits, a small amount. But because the strong nuclear force and nuclear fission is so potent relative to the carbon-hydrogen chemical bond in the coal, you would actually have more energy available to mine and refine the coal down into its thorium and uranium.
Then burn it.
Right. And I'm not joking. That is literally true. A million times. You could have 1,000,000 times more civilization.
What happens... Oh, okay. We have got this hypothetical piece of coal that has a few atoms of this or that.
Yeah.
What happens to the this or that when we burn it?
Coal emits more radioactive pollution into the environment than all the nuclear reactors we've ever had. Because if you're an average coal plant, you might burn between 5,000 to 9,000 tons, that's tons, of coal a day to keep the lights on and to keep your house heated.
Okay.
That means 9,000 tons of coal ash. Nothing goes anywhere. There's always consequences. 9,000 tons of coal comes in, you burn it, you make some heat, make some steam, make some electricity, people use it, they got to heat up their burritos in the microwave. And one of the consequences of that is 9,000 tons of coal ash a day, which emits a lot of radioactivity because there's uranium and plutonium. Well, not plutonium, uranium and thorium in it.
Gotcha. Just as a part of the ash now.
Yeah.
Nothing happened to the uranium and plutonium.
Right. It goes through a furnace. It doesn't care.
Right.
It's nothing compared to a fission or a nuclear reactor. There's no neutron flux in a fire.
Right.
That's a chemical process, not a nuclear process.
Right.
But because of that, because we're digging it up, exposing it to the air, pulverizing it, burning it, breathing it in,
shoveling it around.
Coal is a worse I'm going to say this for the record. February 5th, 2020, coal is a worse radioactive polluter than our nuclear industry. Congratulations. So nature ejected. One way to think about it, think of it like the nuclei. So the nuclei are very big relative to one neutron.
Okay.
The nuclei of those stars as they exploded and destroyed themselves under gravity and energy and all that colossal process. The nuclei acted like a net that caught those neutrons into themselves. They caught it. The neutron could have just flown into outer space and presumably still be there, zipping around, but instead it got caught by
all the stuff the star had already put together.
Yeah, it got caught by a rubidium or a lanthanum atom, and now it's something bigger and then bigger and bigger because there's all sorts of neutrons, and now uranium is floating around in space, and all that energy went, you know what I mean? It could have been dissipated into just pure neutrons in a theoretical sense.
Okay.
But or as photons or whatever, but it's neutrons, and it got caught, and now it's regular matter. Now something that was forged in the heart of not even in the heart of a star, at the moment of a supernova, is now a lump of metal below your feet. Mm-hmm. And that energy is still there. It's like a spring. It's like a spring that wound up. Boom! You in a millisecond, you go boom, and you hold it, and now it's like it's so incredibly intense. There's all that energy. Mm-hmm. And what did the Western world do with that energy?
Kill people with it.
Turn it into bombs. history is going to judge Western civilization as one that said, wait a minute. They looked at uranium and plutonium and they said, I have this metal that if I make the right recipe and if I make the right configuration, in one moment, I could release all of that energy over a civilian population and destroy it in a second. Or what if you slowly metered out that energy?
Right.
I could destroy a city with it, a sphere of plutonium, or I could
Or
power
eat burritos with it.
I could power a civilization with it. Which one's it going to be? We made our choice. That's the fucking Cold War.
It's not a very efficient way to use it either.
We will never.
You know, it's like back to a few